While I get this back together, we're going to go full nerdgasm on this aluminium. I'll edit out the glottal stops, the cognitive stalls, and otherwise disconcerting humanities. This is a die-cast aluminium part. There's a number of parts here, actually. This process is very... there's a lot of science involved. Being as aluminium is quite a new material, but die casting is an old art form, essentially. What they would do is they would machine dies out of H13 tool steel. H13 is a tough tool steel, and it does not erode easily. So when they pour this in, it doesn't get poured into a die. It gets pressure injected into a die. Very high speeds, high flow rates, and around any kind of elements that are squeezed. Of course, when you have a high flow rate, the velocity needs to get amped up, and that velocity erodes away the dies. So they use H13 tool steel to reduce the amount of the longevity of the die itself. If they're just doing short production runs or short prototyping runs, they'll probably use D2 tool steel because it's quite a bit cheaper. Aluminium, the metal, has only been around for a couple hundred years, and it's not until the 20th century, rather, or 19th century. 1800s is 19. Yeah, we'll say early 20th century that it actually came to the fore as a material for making things. Part and parcel of that is that it's extremely abundant, first off, in the Earth's core. I think it's second only to silicon in abundancy, but it is a refractory mineral. That is, refractory is heat resistant. It's very difficult to separate from its ores. A fellow by the name of Bayer, Carl, I believe, was working in Russia on a bunch of stuff for clothing. And part of that is the dyeing process. Well, they would use alumina as a mordant. And mord in French, mordant is a French word, means to bite. Mordant, to bite. And they use that word also in etching, and for PCB etching. You need a mordant, and that means to bite. Okay, so in order to get dye to stick to clothing better, they use this alumina. And the process prior to Carl Bayer coming along was an acid process to get it out of its mineral ore. And then there would be like this, it would be difficult to separate because it would be this sludgy, mushy mess. So he came up with the idea to use sodium hydroxide in an aqueous solution in order to digest these mineral pulps, of course, ore, and then broken down. That would be bauxite is the main ore, and bauxite, consequently, is the official ore or official mineral of Arkansas, of all places, bauxite. Now, well, Arkansas is interesting as well because it had oil at one point, but then they started going deeper and deeper and deeper, and there's a little museum on the outskirts of Little Rock, maybe, Arkansas? One of those towns, anyway. And it's a brine museum. And it's a fantastic museum, actually, for a small town, little shithole place. It's a great museum. And it shows you all about the history of brine. And it is one of the only places on the planet what you get bromine, mineral salts out of the brine. This brine has been sitting in the earth in aquifers deep below where they were getting oil from for millions upon millions of years. So they still use brine. They still pump brine today, and it's a mineral resource essentially. So where was I going with this? Arkansas bauxite. Oh yeah, Bayer process. Okay, so the Bayer process essentially is you take the ore, you crush it up, bauxite ore, you crush it up, you put it in a pressure vessel with aqueous sodium hydroxide. It turns it into alumina. When you dry it out, it forms crystals. So instead of this moopy, gushy mess, what you get with the previous process, this Bayer fella figured out you could get crystals, made tons of money on doing mordants for textiles. I'm not real familiar with textiles, so it comes to the tongue a little slow. Come on the tongue being what it is. Now this fella, far outside his realm of expertise, becomes the master, or rather the father, probably unbeknownst to him, the father of hydrometallurgy, which is the methods and usage of water to concentrate minerals from their ores. So with refractory ores, like I said, they're heat resistant ores. So prior to starting to treat stuff with aqueous solutions, you couldn't get gold out of tellurides. You couldn't get alumina. You couldn't get aluminum out of alumina, or rather out of bauxite. You couldn't get small, minute amounts of gold outside of a quartz pyrite matrix. You know, if it's surrounded by pyrite, this tiny little grains. So what they do is they use hydrometallurgy to get that out. And the way they do that is with noxious witches brews, pressures, and so forth. There's a bunch of different processes, but if you had gold that was in the grams per ton range, we're talking parts per million, you know, fractions of grams per tons. What they'll do is a heap leach process if they have enough ore there. Mining companies nowadays are not looking for a little adit in the ground. They're not looking for a little hobbit hole to mine through. They're looking for a scar from outer space in order to start a mine. So what they do is they'll knock the top of a mountain off that's got parts per million of gold. They'll put it on football-sized fields of, rubber, basically rubber boots, essentially, big rubber mat, double, 2 or 3 layers, and then they put the ore on there in lifts. They run drainage tubes through there just to drip a solution, sodium cyanide solution through. They pick up the sodium cyanide at the end after it has put the gold into solution, and then they can electro-win all of that gold out of there. You'd never be able to economically mine that low a grade of ore until hydrometallurgy came along. Now, a great many of us Western devils use deodorant on a fairly regular basis. I know I do, because otherwise I would smell like a fucking animal. That's a part of having that gene, what gives you waxy earwax instead of flaky earwax, and gives you body odor. Japanese people do not have that gene. They do not have body odor, although they sweat profusely from their face. And they have other drawbacks too. Like they get all red-faced a lot of times when they're out drinking. They get fucking wasty pants as well. If that's because they're missing an enzyme in their liver or not remains debatable. In any case, we are all human. And aluminum, alumina. You use it in deodorant. It's used all over. It's in sandpaper. It's very, very hard. Carborundum, of course, is alumina, which non-bastardos, don't let the bastards grind you down. You say that just about every fucking day, am I right? The other thing they use alumina for is for hydraulic fracking. So with hydraulic fracturing in the shale, certain types of shale have almost 30 or 40% carbon in them. So they're highly organic. Of course, shale is a sedimentary rock. It's essentially a clay that's been solidified, and clays occur in water courses, and in water courses, so algae and diatoms and little bitty creatures. I say dinosaur squeezings, but realistically it's more like ancient algae and so forth. So they fall into the clay and solidify, and then if there's not much oxygen in there, they do not break down, and they'll solidify, they'll metamorphosize into this rock, it's a size, into this rock. Now, all of a sudden, the rock is full of keratin. Keratin? Not keratin like the protein, but there's another word. It means that organic matter, what's been stuck in rock. And that you can get oil and gas from. Oil and gas, very energetically dense. Our modern culture, technology, society is based on the ready availability of energetically dense materials, hydrocarbons. In these shales are full of hydrocarbons, but they're locked in there. If they weren't locked in there, they wouldn't be there. So how do we get them out? Well, it used to be what would happen is we would get the hydrocarbons, they'd be stuck under a lens, a rock lens, in some not metamorphic rock, but some sedimentary rock, but sandstone rock, which was very permeable to these hydrocarbons. So it was easy to get the oil out. In these cases, they're tight gas or they're non-conventional gas. They're stuck in shale. Shale, of course, has smaller particles. It's very difficult for those hydrocarbons to migrate through to come up the wellhead. So what they do is they take ungodly amounts of water, drill a hole, pressurize that water, and hydraulic fracture all of the shale. Now, the thing is, once you release the pressure, the hydraulic pressure, of course, the shale closes back up. So what they do is they use fracking sand to keep the tiny little fractures in that shale open. What is fracking sand? It is pelletized and tiny little pellets of alumina. So what they do is they take bauxite, they hydroxide it under pressure, and then turn it into crystals. Then you can take those crystals of various sizes, grind them down again, make them into pellets under very high pressure and high temperature, and that is fracturing sand. When you hydraulic fracture shale, opens it up, allows the keratin, it escapes me, allows that to move freely through that strata, and the alumina is what is keeping open the pores and fissures and cracks of that shale. Kerogen, not keratin. That's the keratin, of course, is what's in your nails and your hair, and that's a protein. Kerogen is the mineralized carbon in shale, kerogen. Also, that alumina, alumina, when it's used in fracking, is called a proppant. Etymology of words being what it is. Proppant because it props open the cracks. Now, I got you as far as aluminum oxide. That's, it's very hard and it's quite chemically stable, mechanically stable. You use it in sandpaper. You use it every day under your armpits if you're like me, a filthy barbarian. So how do they separate aluminium metal? Well, lots of energy. They pass current through it and it separates into its constituents. But the problem is if you pass current through a solid, it doesn't separate. All it does is it passes current. So that ain't no fucking good. But what they got to do is they have to have it in liquid form. It has to melt. Now, unfortunately, aluminum oxide only melts at 2100 degrees Celsius, which is pretty fucking hot. White hot. It's beyond white hot. White hot in steel is only 1200 degrees. And we're looking at, well, we'll say 2000 off the top of my head. That is pretty fucking hot, partner. So, how do you get it liquid without getting it that hot? Well, it's going to hold it type deal. Because you want to do this in industrial quantities. So what they do is they change the colligative properties of the liquid by finding its eutectic point. Let's see, how can I? Okay, I'm going to give you the example here with salt brine, and I'll show you a little diagram. You know what's serious when I got to draw a diagram? Not that serious. Here we have temperature. And we'll go minus 21. 0.0, however the fuck you do that. And here we'll go 0. Now at minus 21 there's a line, and this is going to be percent salt by weight, or mass. Fucking mass holes. So at, excuse me, at 20, this is 23.3%. And salt, of course, not just any salt, it's the granddaddy of them all, NaCl. Okay, so if you have H2O and salt, it's called brine, which is H2O plus salt. Feel free to fuck off here if I'm driving you bananas. Okay, in this zone here, if we have a lower percentage of salt, say we have 1% salt, what we get is slush. So we get ice and we get salt brine together. Ice and salt brine together. And the lower the temperature, the more ice there is, to the point where all we get is froze, cock, stiff. So this is like sea ice. This is gonna be, it's just solid ice. It's brine turned ice. So this has NaCl crystals in it, crystallized salt, and crystallized H2O rather. Now, as we come over here, we're increasing the percentage of salt in it. Now what we get at a lower temperature, say if we go here at -10, at a certain amount of salt, we get nothing but brine. We get zero ice. And the eutectoid point here, well, eutectic point, which is the eutectoid, is the point at which the lowest temperature coincides with the Goldilocks amount of salt in the brine, which is 23.4%. The lowest temperature you can go with salt water without it freezing is minus 21 C. If you go over, what happens is you get salt crystals and H2O. So this is okay too, you know, when you're salting your sidewalk, but I'm trying to show you here what you can do with the alumina is you add a compound that changes the colligative properties, and what you can do is reduce the temperature at which the entire thing melts. Now recall, as I said, alumina melts at 2100 C. So what do we put in here to reduce the melting temperature? We put in a halide. Harkening back to a simpler time, your kindergarten chemistry class, recall halides are right beside the noble gases. They are the deadliest, nastiest elements of all. The chlorines, the bromines, the fluorides, fluorines, there's another one in there. But anyway, they'll kill you right dead. Every time you overheat a Teflon pan, a canary in the coal mine dies type deal. So those are nasty, just dying to give up an electron. Iodine. It comes in the form of cryolite, which is kind of getting to be a rare mineral, so they synthesize it. And it has a fluorine atom in it. They mix that up with the alumina, and that lowers the melting temperature from 2000 to right around 900 degrees Celsius. And what they do, well, I'll best draw you a picture. They stick that solidified witch's brew of the halide, the cryolite, and the alumina together in a reduction cell. So in the bottom of a reduction cell, for aluminum, you'll have a cathode. This will be graphite. Graphite is excellent as carbon, right? With a little clay. It's excellent because it's a conductor and it's very, very high temperature. It also helps the process because it erodes, or it leaves off, it gives off carbon. So the cathode, of course, is negative, and then we'll have some steel electrodes that'll be the positive, which is the anode. And then what we'll have in here, we'll have a layer. Now consider this is already hot because they keep these hot 24 hours a day. They never shut them down. So this would be molten aluminum. In here, they'll have the alumina and cryolite mixture. Now this alumina is also right full of oxygen. So we take the carbon coming off the cathode, we mix it with the oxygen, we get CO, carbon monoxide, and CO2 off gas into the flute. And then we also get, because this cryolite is in here, we also get the oxidization of the fluoride in here. Now remember, we just added the cryolite in order to reduce the melting temperature. So instead of having this at 2000, now it's 900, less energy. But it off gases something horrible. Hydrogen fluoride. Or no, it's actually hydrogen fluoride, like that. This is deadly, deadly toxic. So this has to go through scrubbers, and I believe they're liquid scrubbers. So they get picked up through water. They get picked up, and that turns into hydrofluoric acid, which is a very, very nasty acid. If I'm not mistaken, it's the acid used to etch glass. But the magic here is done by the electricity to the tune of 15 kilowatt hours per kilogram of solidified aluminum per kilogram. That means that these smelters need to be really close to either a hydroelectric dam or geothermal power, such as in Greenland, and that's where you find all of the Alcan smelters up in Kitimat in, I hear it's pronounced Shitimat actually, in northern British Columbia, as well as in Greenland, these Alcan smelters, because they take a lot of power, and of course they need some corporate welfare. They get cherry rates on their power and so forth. And that is why, children, we must always recycle aluminium. Santa Claus is watching. Yeah, steel only takes 10 times more energy to smelt aluminium than it does steel. And of course, once it's smelted, once it's in the metal form, you don't have that huge energy input. So recycle, 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 or stick it right back into Mother Earth Gaia, and we'll mine the fuck out of that come the adpocalypse.